Hi there, Mr. Sutton here, bringing you the AB Calculus 4-5 Part 1 homework solutions on points of inflection.
For this problem, f is a function that's defined and continuous on this closed interval. If f has relative max at c, and c is between a and b, we want to know which statement has to be true. So we've got these three statements. Let's see if we can eliminate any of them. So f prime of c exists. Well, if we have a relative max, then this is certainly one possibility, is that the derivative exists, and moreover that it's zero. Another possibility, though, is that f prime of c does not exist. For example, if we had a cusp. So you could have a cusp at x equals c, which would also give you a relative max. So statement 1 does not have to be true. Statement 2, if f prime of c exists, then it equals 0. Well, that has to be true. If we have a max there and the derivative exists there, then that means it must be a smooth turnaround, so it has to be 0. Because if you have a relative max, you either have 0 for the derivative or dne. You got to have one or the other. If it exists, then it's got to be 0. So that's a yes. And then for this next one, if f double prime of c exists, then it's less than or equal to 0. Well, that also has to be true. Because this is our second derivative test. So they're saying that if f double prime of c exists, well, that implies that f prime of c exists. Because if f prime of c didn't exist, f double prime wouldn't either. And if f prime exists, then you've got a critical value. You've got 0. And then if you have concave down, you're at the top of a frown. So that would give you a relative max. So this is going to be true if f double prime of c is less than 0. And the equals not so much, but the way this statement reads is they said if f double prime of c exists, then f double prime of c is less than or equal to 0. Well, that means it's true if one of those conditions is met. The less than part is definitely true. So that's enough to say the whole statement is true, so another yes. So then it looks like options 2 and 3 are the only ones that have to be true, so choice E. On this problem, we want to know at what x values this graph has a point of inflection. So for that, since we have the original function, we're going to need to look at the second derivative and see where that changes sign. So first derivative is going to be 15x to the fourth plus 40x cubed. And then taking one more derivative to get y double prime, that's 60x cubed plus 120x squared. We're going to set this equal now and solve for critical values. I can start here by taking out a 60 and an x squared. That's going to leave me with x plus 2 equals 0. So we see this is going to be true when x is either 0 for this first piece or negative 2 for this other parentheses. And that gives us two critical values to do some sign analysis on. So going to our f double prime, y double prime sign chart here, we've got negative 2 and 0. And doing some sign analysis, something less than negative 2, let's try negative 3. Now when you're doing your sign analysis, this 60x squared is always going to come out positive, so you can just kind of ignore it and focus on the x plus 2. Plugging negative 3 into that, that's going to be a negative. And then something between negative 2 and 0, like negative 1. Plugging that in, we've got, let's see, negative 1 plus 2 is positive. Something bigger than 0, like 1, 1 plus 2, also positive. So we see that y double prime changes sign at x equals negative 2. Therefore, the graph y has a point of inflection at x equals negative 2. And then that would give us choice B, negative 2 only.
For this problem, we're given the function f of x equals cosine of 2x plus ln of 3x, and we want to know the first x value, at least the least value of x that's given here, where the graph of f changes concavity. So we're essentially asking, where does f double prime change sign? Where's the first of these values that happens? This is a calculator problem, but we first need to know what f double prime looks like in order to graph it. So let's start with just f prime. So we're going to need the chain rule for both of these terms. We've got cosine of something. Derivative of that is going to be negative sine of the something, so negative sine of 2x. But then we have to multiply by the derivative of 2x, which is 2. So that's going to be negative 2 sine of 2x. for that first term. Next up, for ln, we've got the derivative of ln of something. That's going to be 1 over the something. So that's 1 over 3x times the derivative of 3x, which is 3. So when the dust settles, that's going to be 3 over 3x. And I know I have to take another derivative of this, so I'm going to clean it up a little bit. The first term is fine, but this next term, I can write this as 1 over x, which I can further simplify to x to the negative 1. And I'm only doing that because I'm going to be using the power rule soon, so I want to make my life a little bit easier and avoid having to use a quotient rule here. All right, so taking another derivative, derivative of this first term, derivative of negative 2 sine of something would be negative 2 cosine of something, but then we have to multiply by the derivative of 2x, which is 2. So that's going to be negative 4 cosine of 2x for that first piece. And then derivative of x to the negative 1, we're going to have negative x to the negative 2. And now I want to figure out where this f double prime is first changing sign. So let me go to Desmos for that. So here in Desmos, let me enter this function. I'm just going to call it g, so I have something to call it. And I'll call this, let's see, negative 4 cosine of 2x minus x to the negative 2. So this is what I'm looking at, and we can see that this thing is changing sign all over the place. So we have to just sort of focus on the answer choices they gave us. They didn't give us an official interval, but these answer choices are all clustered between 0 and 3. So that's what I'm going to adjust my window to. Let me make that go from 0 to 3. 0 to 3. There we go. And let me just click on this so I can get my gray dots. And the first place where we're crossing the x-axis is right here. This is 0.932. Let me just put that picture here so we can look at it. So that's going to be, since that's happening at 0.932, that's going to be choice B.
For this problem, we have a function defined as sine of x plus cosine of x between 0 and 2 pi. We want to know the x value where our point of inflection occurs, but it's a specific kind of point of inflection. We want the one where f is changing concave down to concave up. So basically, we're asking at what x value does f double prime change from negative to positive. So let's go ahead and find f double prime and do some sign analysis. F prime, to start us off, is going to be cosine of x minus sine of x. And then f double prime, we've got negative sine of x minus cosine of x. And that has to equal 0 somewhere. This is kind of a tricky one to solve if you've never done one of these before. The idea, though, is that we have to get sine and cosine on opposite sides of the equation and then divide to get tangent. So I'm going to start by adding sine over to the right side here. And then if I divide both sides by a negative, or actually just divide by cosine of x, that's going to give me negative 1 on the one side, and sine over cosine is tangent of x on the other side. So divided by cosine to get this. All right, now you might be wondering, why am I allowed to divide by a variable in the first place? Because cosine of x is an unknown when you get down to it. And what justifies doing this, if you've never seen this before, is that cosine of x and sine of x can't both be 0 at the same time. Because one is the x value, one is the y value of some angle on the unit circle. If they were both 0, you wouldn't be on the unit circle, you'd be at 0, 0. Well, if they can't both be 0, then neither one of them can be 0 because they essentially equal each other here. So that guarantees that we're not dividing by 0, so we can do sine divided by cosine and get away with it. All right, so where does the tangent equal negative 1? Well, between 0 and 2 pi, that happens in two places. One is in quadrant 2 at 135 degrees, so that would be 3 pi over 4. And the other is in quadrant 4, if you just continue down that line through the origin, at 315 degrees, or 7 pi over 4. Going on our number line now, and this is an f double prime line here, we've got endpoints of 0 and 2 pi. So let me just put those on there. So we've got 0 and 2 pi, and then we have the two critical values, 3 pi over 4 and 7 pi over 4. So let's test something in each of these intervals, something between 0 and 3 pi over 4. Well, how about just pi over 2? That's a pretty easy one to test out. Now, normally I'd be cautious about this because pi over 2 makes tangent itself undefined, but f double prime isn't really tangent when you get down to it. It's negative sine of x minus cosine of x, which is defined everywhere. It's not undefined anywhere. So plugging pi over 2 into this, that would be negative 1 minus 0, so that would be negative overall. And then something between 3 pi over 4 and 7 pi over 4, well, how about just pi is an easy one to plug in. So that would be, let's see, 0 minus negative 1, which is going to give us a positive. This last one's a little tricky, something between 7 pi over 4 and 2 pi. Well, 330 degrees, that would be 11 pi over 12. That's between 315 and 360. So this is a little trickier, but the negative sign of that's going to be negative 1/2, so positive 1/2 minus, and that's going to be radical 3 over 2. So 1 over 2 minus radical 3 over 2 is going to give you a slightly negative number. Now, if you weren't sure about this, you actually could have technically plugged in 2 pi, because these signs are going to change every increment of 180 degrees as you go kitty corner to kitty corner on those 45-degree rays there. So if you plugged in 2 pi, this would have been, let's see here, 0 minus 1, which also would have given us a negative. Another reason I'm not as worried about this interval, they just wanted to know the x-coordinate of the point of inflection where the graph changes from concave up to concave down. And that's just this first one right here. Our f double prime is changing negative to positive at 3 pi over 4 only on this interval from 0 to 2 pi. So that means that we really just wanted answer choice B all along. For this problem, we're given the graph of f prime from negative 3 to 6, and then we're suddenly told that h prime is 2 times f prime, and we want to know points of inflection, or how many of them there are on the graph of h on the same interval. Well, before I can talk about h, I need to talk a little bit about f. Taking a look at the graph of f prime, I see that we are changing increasing to decreasing, or decreasing to increasing at 2 spots. That tells me that the graph of f is going to have points of inflection in 2 places. Now, how does this relate to the graph of h? Well, h prime is 2f prime. Basically, you're just stretching the f prime graph that they gave us here vertically. Since I'm stretching vertically rather than horizontally, that means I'm guaranteed that these turnaround spots are going to happen between negative 3 and 6. If we stretch it horizontally, they might be outside that interval, but vertically we're safe. So we're also going to have 2 turnarounds for h prime between negative 3 and 6. That means that the graph of h will also have 2 points of inflection. So answer choice B. For this problem, we have a function that's twice differentiable, and they're saying that the graph of f has no points of inflection. And they're giving us values of f, f prime, and f double prime at 6. Based off of these, they want to know what could be the value of f of 7. So we don't know for sure, but this is just going to be talking about how fast the function is changing and which of these could be a value for f of 7 based off of that. So one key piece here is there's no points of inflection, and also that our second derivative is already negative. Well, if f double prime of 6 is negative and there's no points of inflection, this is basically saying that f double prime of x is negative everywhere. If there's no points of inflection, there's no places where the sign of f prime can change. So we find one negative, that means everything's negative. So we're guaranteed at the very least that f double prime of x is negative on the interval from 6 to 7. Again, it's actually negative everywhere, but all we really care about is this interval, because that's going to get us from the x value they gave us information at to the x value they're looking for information at. So at the very least, we're concave down from here to here. All right, next piece, we need to know if we are increasing or decreasing, because concave down by itself doesn't tell us whether we're going up or down. We could be on either side of the frown. So to figure that out, we need to talk about what f prime is doing. Now we know that f prime is already negative at 6. And they told us that f double prime of x on the interval we care about is also negative. So that means that f prime is decreasing. Well, if f prime is already negative and it's decreasing, that means it's going to stay negative on the interval from 6 to 7 as we move forward here. So summing up what we've got here, f prime is negative, that means we're decreasing. F double prime is negative, that means that we're decreasing at a decreasing rate, so we're going down faster as we go. So based off of that, what could we have as a value? Well, let's just pretend that we have a linear function to start off with. So if this function were linear, then we would be doing essentially 3 and minus 1/2, because that's the slope at exactly x equals 6. And that would give us 2.5. Because we're decreasing at a decreasing rate, though, we're actually going to get a number that's even smaller than that goes down by more than 1/2. So f of 7 is going to have to be less than 3 minus 1/2, which is to say less than 2.5. The only answer choice that's less than 2.5 is A, 2, so that's what we have to pick.
For this problem, we have a function whose first derivative is the square root of x over 1 plus x cubed, and we want the x-coordinate of the inflection point, if it exists, for the graph of f. All right, well, if we already have f prime, to get the inflection point, we need to know where f double prime is changing sign. So we just need to first figure out what f double prime looks like, and then since this is a graphing calculator problem, we're just going to graph it and see where it crosses the x-axis, if anywhere. So what is f double prime going to be? Well, since I've got a quotient that I can't really simplify here, I'm going to use my quotient rule, u prime v minus uv prime over v squared. And let me set up my box and ribbon sort of setup here to organize all this. So for my u, I've got the square root of x, which I'm going to call x to the 1/2 power, just to make it a little easier to take that derivative in a moment. And for the v, the denominator, I've got 1 plus x cubed. So derivative of x to the 1/2, that's going to be 1/2 times x to the negative 1/2. And then for the v prime, I'm going to have the derivative of x, which is 1, plus the derivative of x cubed, so 3x squared. So 1 plus 3x squared. Putting that all together into one function, I've got 1/2 x to the negative 1/2 times all this stuff up here, 1 plus x cubed. And then we're going to be subtracting x to the 1/2 times 1 plus 3x squared. All of that being divided by this v squared here, 1 plus x cubed quantity squared. So this is the monstrosity that I need to figure out where it changes sign. So let me go to Desmos and see if I can find that out. So here I am on Desmos. Let me first enter this in here. I'll just call it g. And that's going to be, let's see here, we need a fraction, so fraction button, the division button, and then we've got 1/2, and then x to the negative 1/2, and arrow down here. Now we've got parentheses 1 plus x cubed, close the parentheses, minus x to the 1/2, oops, and then we've got parentheses 1 plus 3x squared. So half the time on this problem is just entering all of this in. And then finally down here, 1 plus x cubed, all of that squared. All right, let me move this over so I can see my graph. So this is what the graph looks like. And in terms of the interval, we see that all of our answers are between like negative 0.5 and positive 1.5 if we're being really generous. So let me just change my, my window here so that I'm doing like negative 0.5 to 1.5. So that should give me a closer look at what's going on. And I see that there's one intersection point. Let me just click on my function and then click my gray dot. And let me just copy and paste onto the screen what I'm seeing here. So we see at 0.473 there is a sign change from positive to negative. Therefore, that tells us, since the graph exists everywhere except negative numbers, that tells us that we're going to have a point of inflection at 0.473, giving us answer choice B.
In this problem, we're given the graph of f prime, the derivative of some function f, and we said the domain of f is the open interval from 0 to d. We want to know which statement is true. So we'll just go through one at a time and see what we can eliminate. So statement A, f has a local minimum at x equals c. So here's c right here, and we see that f prime is going positive to negative there. Well, if f prime is changing positive to negative, that tells us that f has a local maximum, not a local minimum. So this is a no. Moving on then to choice B, f has a local maximum at x equals b. Well, f prime has a local max at x equals b. As far as f goes, there's nothing about the graph of f prime that would indicate f has a max at this spot. In order for f to have a max, f prime needs to be either 0 or does not exist. This spot is not 0. This is not 0 for the derivative. And it also exists. It's not existing. So there's no way we could have a local extrema of any kind at x equals b. All right, next one. Graph of f has a point of inflection at a, comma, f of a, whatever f of a is. Well, here's the x value a. Now, in order to have a point of inflection, we need a direction reversal for f prime. Prior to getting to point a, f prime is increasing from 0 to a. It's also increasing as you look here after, until we get to b. So since there is no direction change for f prime, there's no point of inflection possible for f. So that's also a big no. All right, so next one. Point of inflection for f at b, comma, f of b. Well, there is a direction change. The f prime is changing from increasing to decreasing at x equals b. So therefore, we do have a point of inflection on the graph of f there. So that's a yes. We're probably going to pick this one, but let's just check out choice E. No harm in that. Graph of f is concave up on the interval c to d. So here's c to d. Now we notice here that f prime is decreasing, which would indicate that we are concave down on that interval, since f double prime would be negative. So that's also a no. So then definitely we can pick choice D with confidence. For this problem, we want to know if the graph of x cubed plus ax squared plus bx minus 4 has a point of inflection at 1, negative 6. What's the value of b? So to figure this out, first let's figure out where the second derivative of this expression equals 0. That's the only critical value we need to worry about, since it's a polynomial and it's not going to be undefined anywhere. Let me take y prime first. So we have 3x squared plus 2ax, because a is a constant, plus b, and that's it. Negative 4 just becomes 0. Now for y double prime, the thing we're going to set equal to 0, we've got 6x plus 2a, and again, that takes on a value of 0 at some point. But we only take on a value of 0 when I plug in the point of inflection. So I'm plugging in the x value 1 in this case. And I see that when I plug 1 in for x, this should come out to a second derivative of 0. Well, what a value makes that happen? I don't have enough information for b yet, but if I at least know what a is, I've got something. So if I subtract 6 and divide by 2, we have an a value of negative 3. So at this point, I can at least go back and plug that in to the original equation here. So y equals x cubed plus negative 3x squared plus bx minus 4. And now that I've got this value plugged in for a, the only variables on here are the x, the y, and the b. And x and y, we actually know what that is, because they said we had a point of inflection of 1, negative 6. Well, since it's a point of inflection, that means that it's actually on the original graph. So I can replace y with negative 6, and all these x's here I can again replace with 1's. So we have 1 cubed minus 3 times 1 squared plus b times 1 minus 4. Let me simplify the right side a little bit now. So this is going to be, let's see, 1 minus 3 is negative 2. We have a minus 4 here, so that's a total of negative 6. So b minus 6, or negative b plus 6, either way. And then if I just add 6 to both sides, I get b equals 0 after all that work. So that's going to end up being choice B.